Myself Sumuka. I'm a student from SVC, currently studying in the third semester of engineering. Today's topic is understanding stochastic processes and Markov chains. What are stochastic processes? A stochastic process is a mathematical framework used to describe systems involved over time with an inherent element of randomness. It involves a collection of random variables indexed by time or another parameter, which represents the states of the system at different points. Key features: randomness. Outcomes are not deterministic but follow a probabilistic model. Time dependency. The process involves based on a sequence of events or a timeline. State space. The set of all possible states the system can occupy. Example: number, symbol, more complex structures. Finance. Stock prices follow stochastic models like the geometric Browian motion. Other option pricing. Example: Black-Scholes model. Weather forecasting. Temperature and rainfall predictions rely on stochastic models to account for uncertainties. Queuing system. Models for systems to customer service, network traffic, or production lines where arrival and service times are random. Stochastic processes. A regular stochastic process is a type of stochastic process where the involved evolution of probabilities over time adheres to a well-defined set of rules. These processes often exhibit consistent patterns or behaviors over time, but will inherit randomness. Key characteristics: transition probabilities. Probabilities of moving from one state to another are defined and may depend on time or the current state. Randomness incorporates inherited uncertainties or variability in the process. Time dependency. Future states depend on the current state and may follow deterministic or probabilistic rules. Regularity. The system exhibits long-term stability in terms of transition probabilities or expected behaviors. State space. The state of possible states can be finite or infinite, discrete or continuous. Applications of regular stochastic processes. Finance. Predicting price movements in stock markets or managing portfolios. Operations research. Optimizing resource allocation in supply chains or scheduling tasks in systems. Healthcare, modeling patient arrivals at hospitals or disease progression over time. Physics and chemistry, understanding diffusion process or molecular interaction, etc. Now, Markov chains. A Markov chain is a type of stochastic process that satisfies the Markov property where the future state of the process depends only on its current state and not on the sequence of past states. This memoryless property makes it a versatile tool for modeling systems where probabilistic state transitions states the possible conditions or positions the system can occupy. Transition probabilities, the likelihood of moving from one state to the other, typically represented by the transition matrix. Markov's property, P of xn plus 1 is equals to x and xn minus 1 and so on till x0 is equals to P of xn plus 1 is equals to x of xn, P of xn and plus 1 is equals to x of xn comma xn minus 1 and so on until x of 0 is equals to P of xn plus 1 is equals to x of xn. Future state depends only on the present state. Types of Markov chain. Discrete time Markov chain DTMC. State change at discrete timelines. Continuous time Markov chain CTMC. Transitions occur at random and continuous time arrivals. Finite or infinite state spaces. A chain with a limited or infinite number of states. Regular Markov chain. A chain where it is possible to reach any state from any other state after a certain number of steps. Key properties: irreducibility. Every state is reachable from one other state. Periodic or versus aperiodic. States return cyclic, that is periodic, or at a regular interval. Stationary distribution, the probability distribution over states that remains unchanged as the process evolves. Absorption states, states that once entered cannot be left. Applications: finance, predicting credit rating and default risks; machine learning, hidden Markov models (HMMs) for speech recognition and sequence modeling; operations research, optimizing supply chains and resource applications; biology and medicine, modeling gene expressions, disease progression, patient flow in hospitals. That's all for this video. Thank you for watching.